Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Cross-function reentrancy. When it comes to check effects interactions on one function, that is not enough when two functions share the same state. During the callback, the attacker calls a different function that still trusts the stale balance. So what exactly is the trick? During withdraw's callback, call transfer to move the not yet zeroed balance to a second account. What is the result of this hack? Funds are withdrawn and transferred. That is double spending. The balance is spent twice. What is the fix in this case? Apply check effects interaction across all functions sharing state or protect the whole group with one mutex. Today we are going to understand cross-function reentrancy by actually deploying the contract and exploiting the cross-function reentrancy. So what are we going to do? First, we will deploy the VulnerableBank in which the honest account deposits 5 ETH. Then in the next step, we will deploy CrossFunctionAttacker. In the third step, the attacker calls seedAndAttack. In the fourth step, the partner.cashout account is called. In the fifth step, we show that the attacker plus the partner account now holds approximately 2 ETH from a 1 ETH deposit. Then we are going to repeat step 1 to 5 against SafeBank smart contract, which implements the reentrant modifier on both transfer and withdrawal function. When we do this, call to the transfer function reverts because now it is sharing a lock or the mutex is shared, such that when withdrawAll is called, the status is set to entered, and when transfer is called, the status is still entered and hence the transaction reverts. Let us go ahead and understand the contract. Here we have our vulnerable contract. Now this vulnerable contract implements iBank, which is an interface which has 4 functions: deposit, withdrawAll, transfer, and balance off. It has a state variable called balance off, which is a mapping from address to UN256. Whenever we call deposit, the balance of mapping is updated with the amount of ETH that we are depositing in the VulnerableBank smart contract. Having a look at withdrawAll function, so what it does, first it fetches the balance from the balance of state variable. It checks the balance must be greater than 0. If yes, it makes an external call using message.sender.call. When this external call is made, if this is made to an externally owned account, there is no harm. The process will work as expected and the caller will get their deposited ETH. However, if the message.sender is a smart contract, then we have problems. So we are going to do exactly that. At last we check either the transfer succeeded and then we set the balance to 0. This is the classic reentrancy attack pattern in which the state variable is updated after the external call. Let us take a look at the cross-function attacker smart contract. Now inside cross-function reattacker in the constructor, we are setting the bank address in the bank variable. So our bank variable is nothing. It is iBank, which is this interface. So once this is set, we can call all the different functions of the VulnerableBank smart contract. Imagine set partner to be your friend's account in which the attacker hacks the bank and then sends 1 ETH to his friend's account. Then we have the seedAndAttack function. Inside seedAndAttack, the attacker first calls seedAndAttack with 1 ETH. So what it does, it checks that the message.value must be greater than 0. If it is greater than 0, then it will call bank.deposit. Once it calls bank.deposit, so what exactly bank.deposit does, it updates the state variable and sets the balance of the cross-function attacker smart contract to whatever the value, in our case 1 ETH. After that, the attacker calls bank.withdrawAll. Once the attacker calls bank.withdrawAll, The balance of state variable is read. The amount is set to 1/8. This required check passes because 1 is greater than 0. Then an external call is made. As I said previously, if it could have been an externally owned account, there is no problem. But in case of a smart contract, there is a problem. Because whenever you are transferring ETH to a smart contract, that call goes into the smart contract's receive function. In case of the cross-function attacker, have a close look at the receive function. First, it checks the status for reentered. If it is not, then it will set reentered equal to true. Once that is done, in the next step, it calls the balance of function with address of this. Now, whenever you want to access the smart contract's deployed address inside its own code, you use address of this. So first it calls bank.balance of address of these, which returns 1. So 1 ETH is stored into stale. After that, it goes ahead and call or makes a low level call to the bank smart contract, and then it calls the transfer function. Now when it calls the transfer function, here we have the transfer function. So from here, the call to transfer is made. As soon as the call to transfer is made, it checks the balance of message.sender must be greater than equal to amount. The attacker is smart enough to pass in the amount such that this check passes because this state variable is not yet zeroed yet. Remember, the external call went from here, and then from the receive function, the transfer is called, and at last, the state variable is updated. So the state variable is not yet zeroed out. So this check passes. Then what it does, the balance of message.sender is subtracted with the amount the attacker sends exactly 1 ETH. Now it is 0, and the balance of 2, which is the attacker's friend, is set to 1 ETH. So what exactly the attacker has done? First, stolen 1 ETH from here, and since the state variable was not yet updated, then again called the transfer function, which also depended on the balance of state variable, and transferred 1 more ETH to his friend's account. So this is cross-function reentrancy, wherein two different functions depend on the same state variable without any check effects interaction pattern or non-reentrant modifier. Let us now have a look at the SafeBank smart contract. The SafeBank smart contract implements the iBank interface and ReentrancyGuard. The deposit function is the same as that of the VulnerableBank. However, the withdrawAll function implements the non-reentrant modifier. It follows the check effects interaction pattern. How do we know that? The state variable is zeroed out and then the external call is made. So what happens when the cross-function attacker now tries to call this function again? First, it calls withdrawAll. From withdrawAll, the balance is set to 0. Then it calls message.sender.call, and that lands into the cross-function attacker's receive function. From within the receive function, it then calls the transfer function. However, ensure we have applied the non-reentrant modifier. That is, from here, when withdrawAll was called, the non-reentrant modifier invoked, which set the status to entered. And then from line number 85, again when transfer was called, the non-reentrant modifier was invoked. And then it got failed at line number 119. Since the status was already set to entered by withdrawAll, here we are checking the status is not equal to entered. In this case, the transaction will fail with the error ReentrancyGuard reentrant call. Thus, in order to mitigate the risk of cross-function reentrancy, you must ensure that you are applying the non-reentrant modifier on both the functions and not only one function. Let us now head over to the Remix IDE and try out the cross-function reentrancy hack, in which first we will deploy the VulnerableBank, then the cross-function attacker, execute the hack. In the next step, we will deploy the SafeBank and again try to hack the SafeBank from the cross-function attacker smart contract. Step 1, we have to deploy the VulnerableBank and then deposit 5 ETH into the VulnerableBank smart contract. Let us do that. First, I'll copy this code, come to Remix. On Remix, create a new file. That file will be CrossFunction.sol. Then paste the code. Close, done. Here the compiler is 0.8.20. Let us check the selected compiler. 0.8.34. The contract can compile because we are using a cap sign. Let me click on compile cross function. The contract got compiled. So first step is we have to deploy VulnerableBank. Let us go to deploy and run transactions tab. Click on this. From here, we are going to select the VulnerableBank smart contract and hit deploy. As you can see, the VulnerableBank smart contract is deployed. Now we have to deposit 5 ETH into the smart contract. So I'll select account 2, and from account 2, I will deposit 5 ETH into the VulnerableBank. So here we have the deposit function. The amount is 5. Change the unit to Ether instead of Y. So choose Ether. Click on transact. After sending, so I have sent 8 ETH instead of 5. And you can see those 8 ETH is being now reflected into the smart contracts balance. We are done with step 1. In step 2, we are going to deploy the cross-function attacker and pass in the VulnerableBank's smart contract address. First, change the account to account 1. Then select CrossFunctionAttacker. From CrossFunctionAttacker, here you have to input the bank address. This is our VulnerableBank address. Here it is the copy icon. Click on this. Come back here, paste the address and click deploy. If we scroll down, here we can see the cross-function attacker is now deployed. After that, we have to deploy the partner smart contract as well. Let us do that. Again, select partner, paste in the bank address, which we have already done. It ends with 138. Here in the ending, we have 138. Click on deploy. After that, we have to call the setPartner function from within the CrossFunctionAttacker smart contract. Let us do that. Select the function setPartner, copy the address of the partner contract, paste that address here, and click on transact. As you can see, we have set the partner account in the CrossFunctionAttacker successfully. We are done with step 2 as well. Now in step 3, we are going to call attacker.seedAndAttack. This is our CrossFunctionAttacker. Select the function seedAndAttack. From here, you must pass the value as 1 ETH. So if I call, say this with 1 ETH, remember account 2 deposited 8 ETH. Hence its balance is 91.99 ETH because some ETH were spent as transaction fees. Now we are going to call seedAndAttack from account 3. Account 3's balance is 100 ETH. After the attack, the partner contract, it has 0 ETH. So it must show the balance as 1 ETH, and our CrossFunctionAttacker contract should also show the balance as 1 ETH. It is as good as we are depositing 1 ETH but withdrawing 2 ETH because of cross-function reentrancy. Let us go ahead and do that. The next function we are going to invoke is seedAndAttack. Let us do that. Here I will pass in the value as 1 Ether. When we call seedAndAttack, after that the balance of CrossFunctionAttacker will go to 1 ETH, whereas the balance of partner smart contract will be set to 1 ETH inside the VulnerableBank smart contract. Prior to the hack, let us copy the partner contract address, go to the VulnerableBank contract, Select the function balance of, paste in the partner's address, click on call. Right now it is 0. Now let us go and execute the hack. The function is seedAndAttack, value is set to 1 ether. After the hack, the cross-function attacker must show 1 ETH and the balance of the partner account should also show as 1 ETH. Click on transact. The transaction has gone through successfully. The balance of cross-function attacker is 1 ETH. Now let us scroll up and invoke the balance of partner account. If I click on call, now the balance of the partner account is set to 1 ETH. And if we check at cross-function attacker, its balance is also 1 ETH. So ideally, the cross-function attacker has deposited 1 ETH and withdrawn 2 ETH from within the partner smart contract. Now let us call the cashout function. Click on transact so that 1 ETH is now moved to the partner smart contract. If I go up and again invoke the balance of the partner smart contract, it is now set to 0. So this is how cross-function reentrancy works. Let us now try to deploy the SafeBank and try the same hack. In this case, the hack will fail. First, deploying the SafeBank, click on deploy. It is deployed. After that, we will deploy the cross-function attacker. Copy the SafeBank address, paste in as the bank address, click on deploy. The cross-function attacker is deployed. After that, let us check the bank address. Yes, it is set as expected because the SafeBank address is 99C ending with 1960. That's what we see here, ending with 1960, starting with 99C. Then we will call the set partner. Prior to that, we will deploy the partner smart contract. Click on partner. Again, copy the SafeBank address, paste it over here, click on deploy. Now the partner is also deployed. Let me copy the partner smart contract address and invoke the set partner function inside the cross function attacker. Click on transact. It is done. Now let us verify that partner address is set as expected. Click on call. It is C0322 ending with 395A. C03 ending with 395A. So that's done. In the SafeBank, invoke the deposit function and deposit 5 ether. Click on transact. We haven't changed the currency to ether, hence only 5 vibe has been deposited into the SafeBank. Let us change that to ether. Click on transact. Now you can see the balance is 5.0005 ETH of the SafeBank. Coming to cross-function attacker, click on seedAndAttack. Set the amount to be say 1 ETH. Notice the remix terminal. In this case, the transaction must fail. If I click on transact, here it shows transact to cross-function attacker.seedAndAttack errored, error occurred, revert. The transaction has been reverted to the initial state. Reason provided by the contract, send failed. If we check SafeBank's contract, here we have SafeBank. From here, we are making the external call. Once we make the external call, it lands into cross-function attacker's receive function. From within the receive function, the reentrant is set to true. Then it internally calls the transfer function. When it calls the transfer function, that time the transfer function lands onto the non-reentrant modifier. So the code actually fails over here inside the non-reentrant modifier, this line. However, since it was invoked from within the receive function and the call to the receive function was made by this line number 141, message.sender.call. As this got failed, so it checked the OK boolean value, it returned false, and hence the contract returned send failed. So this is how you prevent cross-function reentrancy, in which first you implement check effects interaction pattern and then apply the non-reentrant modifier. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.